So we were sort of in the middle of part of a story, and the story is about why matrices are like numbers, basically, right? So remember that we started off by saying that matrices satisfied, commutative property for addition, associative property for addition. They satisfied a bunch of properties, although they did not satisfy the commutative property for multiplication. And then we did some proofs, right, proving most importantly that matrix multiplication was associative, right? And then what we closed up with was that matrices have something like the number 1, right? The number 1 has a sort of special role. When you multiply by it, then nothing happens, right? And we said that there is a matrix that does this. When you multiply by it, nothing happens, and that's what we call the identity matrix. It's a diagonal matrix that has 1s down the diagonal and zeros elsewhere, right? And that's basically where we stopped. We said that to sort of finish up the story, we have to talk about these things called multiplicative inverses. So multiplicative inverses. So these are the analog of reciprocals of numbers, right? So back in the real numbers, right? Back in the real numbers, as long as you're not 0, right? As long as a is not equal to 0, then you know that there exists some number called a inverse in R with the property that a times a inverse is equal to 1. Right? I don't remember if I introduced the backwards e. The backwards e means there exists. There exists. There exists. Okay. So, right. So this is right. You have some number. It's not equal to 0. You can divide by it. Right. And this is useful because if you have something like ax equals b, then you can divide on both sides. Right? You can multiply by a inverse on both sides. You say that x has to be x would have to be a inverse b. Right? So you can solve. This thing allows you to solve this sort of equation. Okay, and so you're hoping that something like that will happen for matrices. Okay, everybody following? Okay, good. Okay, so so this motivates the following definition. Let A be an n by n matrix. If there exists a matrix B, also n by n, with the property that AB and BA are both equal to the identity matrix, then we say A is invertible. Then we say A is invertible. A is an invertible matrix. Yes, Avery.
I'm sorry. What is if something?
So that's my backwards E.
Oh, okay.
Again, if there exists a B with this property, then we say that A is invertible. Okay, so if there's somebody that you can multiply by and get the identity matrix, then we say that the matrix is invertible. Okay, and that and we call the multiplicative inverse. Multiplicative inverse of A. We usually just say the inverse of A. Yes, Avery.
So in some of the homework, I was wondering this for 1.4.
Yeah.
It was setting things equal to 0, I think, but it was kind of an italicized capital O. Does that still mean 0?
That's the 0, but that's the 0 for matrices. So the 0 matrix.
Okay, and then I is just identity.
Yeah.
Matrix.
Yeah.
Okay.
So the sort of large 0 is the analog of the number 0. The I is the analog of the number 1. Okay. So matrices, these guys are matrices, these guys are numbers, right? So we call B the multiplicative inverse of A, and denoted as A inverse. So that's the notation for it. Yeah.
Is there a reason we're only doing this for a square matrix that's n by n instead of...
Well, so you could have, let's see, so well, one thing is that if you want this to happen, then it has to be square,
Okay.
right? So you can certainly deal with, you can certainly talk about it in that case if it's not square, but we want this sort of thing to happen, and so we're going to stick with square matrices. Yeah. Okay. So let me give a simple example. Like if you take the matrix 0, -1, 0, -1, 0, -1, right, and you multiply it by itself, well, you get 1, 0, 0, 0, 1. Okay. So this is this matrix is its own inverse, right? This matrix is its own inverse, right? I have a bigger example, 1, 3, -2, 2, 5, -3, -3, 2, -4, 14, -8, -1, -17, 10, 1, -19, 11, 1. And I don't know if you want to do it, but if you multiply this thing out, then you'll see that you end up with the identity matrix. Yes.
Wait, I thought the identity... Oh, never mind. I got confused for a second.
That's okay. That's okay. What were you thinking?
I thought the identity matrix was the 0 matrix for
No.
a second.
No, my
And
God.
I got very confused.
Yeah, no. The identity matrix is the analog of 1. Yeah. Okay, so anyway, just a simple idea, right? You have some matrix, and then there's some other matrix you can multiply by and get to the identity matrix, right? And that guy's called the inverse matrix, right? So this guy is A, and this guy is called A inverse, right? Right, and you see that that if we called this guy B, then this guy would be B inverse, right? That if this is the inverse of this, then this is the inverse of that, right? In other words, the inverse of the inverse is your original matrix, right? The inverse of your inverse matrix is A. Okay, so one small comment is the term the inverse justified. Right, we call it the inverse. Is there only one inverse? It turns out that there can be one. So could there be two different matrices, B and B prime, that are both the inverse of A? And the book gives a sort of funny argument to show that this couldn't happen. They say, well, the answer is no. No. Consider this product, BA, B prime. Okay. Say, okay, well, suppose there are two guys and they both act like A inverse, right? They both, when you multiply by them, you get the identity matrix. Okay. So that tells you that B times A is the identity matrix. right? But you also know that A times B prime is the identity matrix, right? Suppose B and B prime are both inverses, right? Then what would happen? Well, B times A is the identity, so this is equal to B prime, right? Right? B times A is the identity, so this thing can be written as the identity times B prime, but that's the same as B prime, right? A times B prime is the identity, so this is B times the identity, but that's B, right? And so B prime must be B, right? If they both act as the identity matrix, both act as the inverse matrix, then they must be the same matrix. Everybody okay with that? Any questions? Yes, Dan.
What if they're all the identity matrix? Or
What
would
if-
that not be an inverse then?
What if all these guys are the identity matrix?
Then wouldn't it work?
So the question is, could there be two different matrices
Never mind.
that are both the inverse matrix? Okay, it's true, yeah, but then you're saying that they're the same to begin with, right? We're trying to show that they cannot be different. Okay, so we don't want to start off by saying that everything is the same. Yeah. Okay. Yeah. Okay. But yeah, that would certainly work, and that just goes to show you that the identity's inverse is itself, right? Okay. Okay. Back here, I should have made one comment, which is that sometimes you'll see this term non-singular. Non-singular. Okay, so the book uses both of these terms. Singular means not invertible. Non-singular means invertible. Okay. Singular means not invertible. Non-singular means invertible. Okay, so for me, I don't like these terms singular and non-singular because I like the terms invertible and non-invertible. They seem more descriptive to me, so I almost never use them. Okay, let's go on. Okay, so another observation is that if A and B square matrices are both invertible, then the product of them is also. The product is also invertible. So any product of invertible matrices is still going to be invertible. Okay. And the way you see it, why? Suppose you have this matrix. Can anybody see immediately some other matrix that you can multiply by and get the identity matrix? This times what is equal to the identity matrix? Can anybody fill in the blank there? The inverse of A times the inverse of B? Other guesses?
Inverse of B times inverse of A.
Inverse of A times inverse of B times inverse of A? Yeah, that one will work actually, right? And you see why it does. Right? The inverse of B times the inverse of A, you're going to get, what would you get? Well, you get A times the identity matrix times the inverse of A. But that's the same thing as AA inverse, right? Which is the same thing as identity. Okay. So you can, why is it invertible? Because you can make the inverse. The inverse, right? The inverse of a product is the product of the inverses in the reverse order. Okay, everybody all right? Okay, so let me have you do an exercise. This is problem 14 in the book. So number 14. Suppose that A and B are n by n matrices, and AB is equal to A. Okay. Then if B is not the identity matrix, then A is not invertible. Okay. So you know that AB equals A, but B is not the identity matrix, and you want to explain why that forces A to be a non-invertible matrix. Okay. So think about that for 1 minute or two, and see if you can come up with an argument explaining why A could not be invertible, or has to be non-invertible. And I'll go walk around outside. Somebody nearby and say, I'm thinking like this, or I have some idea, or I have no idea. That's okay? Yeah. So please put away your phone. This is not time to use your phone. Okay, who would like to say what they're thinking? Anybody have an idea? Why must A be non-invertible? Lizzie.
My idea was that if you multiply both sides of AB equals A by A inverse, then you get B equals the identity matrix, which is not true.
Great,
So
that'll do. That'll do. So certainly you can say, okay, well suppose A is invertible. Suppose A is invertible. Right? But then, since AB equals A, we know that A inverse AB equals A inverse A, right? But that would imply that B is the identity matrix. But also, B is not the identity matrix, right? So there's a contradiction. Okay. So this is so-called proof by contradiction, right? Proof by contradiction. Right. You assume that the thing that you're trying to show is false, and then try to end up with nonsense. Okay. Okay, any questions? Any questions? Yes?
Would you sell another way that's like not a...
Not a proof by contradiction?
Yeah.
Let's see. If B is not equal to I, then A is not equal to I can't think of any way at this point. Yeah. After a little while, we'll have more tools, and we can do it. This is probably the easiest way. Listen, yeah.
X with the 4 dots means contradiction.
Yeah. Yeah, so, sorry, this is the contradiction symbol. Contradiction. Some people write like this. They use this simple contradiction. I think there's some other symbol, but I don't know. Yeah.
Is the inverse of A times A the same as A times the inverse of it?
Yes. Yeah. Yeah. So that was part of our definition of the inverse. So the inverse is the matrix that satisfies this. Oops. The inverse is the matrix that satisfies this. Right. So in either direction, you get the identity matrix. Okay. Later on, we'll see that if these guys are square matrices, and one of these holds, then actually both of them will hold. Okay, but we can't show it right now. Okay. So we're gonna take a little bit of a digression at this point. So to something called proof by induction. So proof by induction. So this is a type of proof that we're going to need a lot. We're going to use over and over in the next week or so, and for the rest of the term. And it's something that you can use. It's a useful tool. Okay. So the idea is this. Say you have an infinite sequence of claims that all of which you want to prove true. Okay, you've got an infinite sequence of claims. Let's call them claim 1, claim 2, claim 3, etc., etc. Okay, so you've got an infinite sequence of claims, and you want to prove that all of those claims are true. Okay. So proof by induction is one way of proving them all true simultaneously. Okay. One can prove. So you try, instead of trying to prove them one at a time, you try to prove them all in one fell swoop. Okay. So proof by induction is the following strategy. One, prove that the first is true. So prove that the first is true, and prove that, in general, the truth of one case, of any case, Cn implies the truth of its successor case, Cn plus 1. Okay. That is, i.e., prove that if Cn is true, then Cn plus 1 is true. For all n. Prove that for whatever n you choose, if that n is true, then the next case is also true. Okay. And if you can prove both of these together, then that will show that all the claims are true simultaneously. Okay, right? Because you see that the first one is true, and you know that the truth of any one of them implies the truth of the next one, right? So C1 being true implies that C2 is true, right? But then you know that C2 is true. Well, again, by part 2, you know that the truth of any one of them implies the truth of the next one, so that means that C3 is true. That means that C4 is true, and so on and so forth. Okay, so you prove this one concrete fact, one concrete case, the first one. And then you prove this general fact about all the things, that if this guy is true, then the next guy is true. If this guy is true, then the next guy is true, right? And this guy being true means that the next guy is true, which means that the next guy is true, which means that the next guy is true, and so on and so forth. Okay, so that's the strategy for proof by induction. How many of you have not seen it before? Okay. Okay, so some of you have not. That's okay. So the typical example. So here's the standard example. Standard example is the following set of claims that the sum of numbers, the sum of I from I equals 1 to n is n plus 1 over 2. Okay. So that is, if you add 1 plus 2 plus 3 plus up to n, you're going to get n times n plus 1 over 2. Okay. So the first claim is that, claim 1 would be that 1 equals 1 times 2 over 2. Right? Claim 2 would be that 1 plus 2 is 2 times 3 over 2, and so on and so forth. Okay, or claim 100 is that 1 plus 2 plus blah 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 up to 100 is 100 times 101 over 2. Right. Okay, so this is what we have here is claim n. Let claim n be this claim for each n in the natural numbers. Okay. This is a famous formula. The story that goes with it is that when Gauss was 8 years old, his class was being noisy, and the teacher said, "Everybody, be quiet. Your assignment is to add up all the numbers from 1 to 100." And supposedly Gauss, while everybody was groaning and adding numbers, Gauss was just sitting back and thinking, and then after a minute, handed in the number 5,050. Having either discovered the formula or seen the pattern that if you add the first and last numbers, and then the second and second to last numbers, and the third and third to last numbers, you always get 101, and there are 50 pairs of them. So let's see the pattern. Okay, so suppose we have this infinite sequence of claims, and we want to prove them all true. Well, if we want to do it by induction, we'll prove the first one, and then we prove the general statement. Okay, that one case implies the next. Okay, so the first one is definitely true, right? 1 times 1 is equal to 1 times 2 over 2. So we'll do proof by induction, proof by induction. So one case n equals 1 is definitely true, right? Because 1 equals 1 times 2. Okay. And then we need to show that, assume that C sub n is true. And let's show that then Cn plus 1 is true. So say, okay, well, we want to show that 1 plus 2 plus blah, 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 up to n plus 1 equals n plus 1, n plus 2 over 2. Okay. But we're allowed to assume that we have a formula for Cn, right? We're allowed to assume that the nth formula is true, right? So what do we know about this? So we know that the sum of numbers from 1 to n, we know that the formula for that is okay, right? So by inductive hypothesis, this is how you say it. By inductive hypothesis, that's sort of the formal language. By inductive hypothesis, we know that 1 plus 2 plus up to n is n times n plus 1 over 2. So we get, so 1 plus 2 plus up to n plus 1 must equal n times n plus 1 over 2 plus n plus 1. Right? And then you just do a little bit of arithmetic, right? Say, well, that's the same thing as n plus 1 over 2 plus 2 n plus 1 over 2. You distribute out the n plus 1, you get n plus 1, n plus 2 over 2. Right? Okay. Okay, so, and that's the end of the proof by induction, right? Proof by induction, so right, you prove the first case, and you prove that the truth of any case implies that of the successor case. Okay, so that's the end. By induction, it's true for all n, for all natural numbers. Okay, so just remember this sort of strategy. We're going to see it a lot pretty soon. Right? In order to prove an infinite sequence of statements, it suffices to prove two parts: that the first one is true, and that if any one is true, then the next one is true. Okay. Any questions? Those of you who haven't seen it before, or those of you who have, and anybody have questions? Okay, let's go on. Okay, so the next section is called elementary matrices. Elementary matrices and invertibility. Okay, so we just talked about these things called invertible matrices. It turns out that invertible matrices can be viewed from many different points of view. Okay, so that is, we're going to sort of, along the way, while we're sort of developing our story of linear algebra, along the way we're going to make more and more observations about invertible matrices. It turns out that we can understand invertible matrices very well, and from many different viewpoints. Okay, so okay. Okay, so okay, so we'll start off with a simple observation. Okay. So observe So remember what we said at the beginning, that if you do elementary row operations, we had these operations you could do to the matrix, and they didn't change the solution set, right? You could switch rows, you could multiply by row by a non-zero number, you could add a multiple of a row onto another, right? And none of those things change the solution set. Okay, so now we're going to make sort of the ultimate observation. Let AX equal B be an n by n linear system. Okay, and you notice in my notes, I'm starting to get a little sloppy, and I just write like this. So I think at this point I got tired of using bold notation, and figured that you know what I mean. It's just some vector. Okay, but anyway, I'm just going to start getting sloppy at this point. Okay, so let AX equals B be an n by n linear system, and let M be an n by n matrix. I'm sorry, an m by m matrix. Okay. Claim if M is invertible, then the system AX equals B is equivalent to the system MAX equals MB. Okay. In other words, has the same solutions, the same solution set. Okay. Does anybody see? Can anybody see why that's true? Like, suppose that x naught. No. Suppose that v, the vector v, solves ax equals b. Okay. Do you see that v also solves max equals mb? Yes. Yes, Ellie? No? Yawning? I'm sorry? I don't want to just talk to you, Reed. Let me, anybody else other than Reed see that this, right? If V is the solution of this, then V is also a solution of this. Anybody other than Reed see it? Yeah, Devin, right? Why? Well, if AV equals B, then just, what do you just multiply both sides by M, and you see that MAV equals MB, right? So if AV equals B, certainly MAV equals MB, right? So V is a solution, so V solves the second system, MAX equals MB. Right, Avery?
This might be wrong, but in this case, I mean, the first thing that came to my mind is that M could just be a scalar.
M is a matrix. M is a matrix.
Could it still, like, since we're talking in terms of matrices, couldn't a matrix that has no variables still be a scalar, or no?
No, we actually really want it to be a matrix.
Okay.
Like it's an m by n invertible matrix. Yeah. I mean, it's true that, if this matrix is, some number times the identity matrix, right? Then you can, you can multiply both sides by that number, right? Yeah. But we really want to talk about, we really want M to be an invertible matrix. And what about going backwards? What about going backwards? Suppose you know, so I'm going backwards. If you, going backwards, so conversely, if V solves MAX equals MB, then, right, you see that you can get back to the original equation by Lizzie? Ross?
Dividing by m.
By multiplying by the inverse of m. Yeah. Don't say dividing by. We don't say that. but yeah, basically, exactly. So multiply by the inverse, right? Then this equals that, which is to say that AB equals B. Right? So you see that any solution that this system is equivalent to that, right? They have the same solution sets, right? Any solution of this is a solution of that, and vice versa. Okay, so this is like the ultimate statement about not changing the solution set, right? Right. Previously, we said if you switch two rows, then that doesn't change the solution set. We had a few sort of simple statements about operations that didn't change the solution set. Now we're saying that if you multiply by an invertible matrix, that doesn't change the solution set. Okay. But in fact, it turns out that those three simple statements are included in this claim, and in fact are equivalent to this claim. We'll see. So okay. So second observation. Elementary row operations correspond to invertible matrices. Okay, so I'm going to say this in English. We said earlier that if you do an elementary row operation, hold on, people are still writing. We said earlier that if you do an elementary row operation, you don't change the solution set, right? And here we're saying if you multiply by an invertible matrix, you don't change the solution set. Okay. What we're going to say right now is that doing an elementary row operation can be accomplished by multiplying by an invertible matrix. Okay, so that these things actually just are contained in this statement, right? Doing these elementary row operations actually corresponded to some multiplication by some invertible matrix. Okay, so these are subsumed in that statement. Okay, so let me just give you the example of how to do it. To switch row 1 and row 2, just switch those rows in the identity matrix and multiply by the result. So if I take the identity matrix and I switch the first two rows, right, and I multiply some matrix by the transformed identity matrix, you see what happens, right? I'm going to get A21, A22, A23. A11, A12, A13, A31, A32, A33. Okay. So this is the I with R1 and R2 switched. Okay. And the same thing happens for the other transformations. So similarly, for multiplying a row by some non-zero constant and changing a row to itself plus some multiple of another row. Okay. If you do this to the identity matrix and then multiply by that matrix, then it's the same thing as doing this operation. So these operations can be accomplished by matrix multiplication. Definition. The matrices obtained from I by a single row operation, single elementary row operation, are called elementary matrices. Okay, so this, for example, is an example of an elementary matrix. Yeah, Lizzie.
Is the inverse of the identity matrix also the identity matrix?
Right, because if you multiply by the identity matrix, you get the identity matrix. Okay, let me finish off with just one last remark. Every elementary matrix is invertible. Every elementary matrix is invertible. Just take the matrix corresponding to the elementary row operation that undoes the other. Oops. Okay, right, like, if I took one row and I switched it with another row, well then, that operation undoes itself, right? So just use that same matrix, multiply it by itself, and you get the identity matrix, right? Or if I multiply a row by a non-zero scalar, well then, multiplying the same row by 1 over the scalar will undo it, right? So, that corresponds, the elementary matrix that corresponds to this will be the inverse of this guy, right? So just use the matrix that corresponds to the operation that undoes the other operation, right? If I take a row and add on, alpha copies of another row, oops. And if I add on alpha copies of another row, well, what should I do? What's the operation that'll undo it? I've added on alpha copies of row J, so I want to subtract off. Yes, thank you. You want to subtract off alpha copies of row J, right? And that would be the inverse operation, right? Okay, so like, if I have one elementary row operation that adds on 5 copies of row 1, the other guy is going to say, I'd like to subtract off 5 copies of room 1. Right? And those would be inverse matrices to each other. Okay. Okay, that's it for today. I hope you get some sleep when you go home.